Hi scholars, you chose that I read the text to you, which is fine. Just make sure your notes are open and so you're ready to take notes as I'm reading. Plastics are polymers. What makes plastics different from other materials, such as glass and aluminum? The answer is found in the wide variety of plastic compounds that can be made from chains of carbon atoms. Scientists make new plastics by designing compounds with a wide variety of properties. The majority of plastics used to make products are synthetic. This means that they are made in laboratories and factories, and they do not exist in nature. The first plastic was developed in 1907. Some natural polymers include the cellulose that makes up wood and cotton, the protein atoms that form strands of human hair, and raw rubber that is collected from rubber trees. Plastics are part of a larger category of compounds called polymers. A polymer is a substance made up of thousands of repeating small molecules. The prefix poly means many, and the word polymer means many parts. The small molecules that repeat in a polymer are called monomers. The prefix mono means one, and so a monomer is one part. Your teacher, modeled the formation of a polymer from many monomers when she attached paper clips to make a long chain. Each paper clip represented the monomers that bonded together to form a polymer. The long chain of paper clips represented the polymer. Take polyethylene, for example. The plastic that was color-coded red in our lesson 16, that was polyethylene. Polyethylene means many ethylenes, and it is a chain of ethylene molecules. The ethylene molecule is the monomer. Adding the prefix poly to the name of a monomer forms the names of many, many synthetic polymers. Think about the other plastics you learned about. Polystyrene, a chain of styrene molecules, polyvinyl chloride, a chain of vinyl chloride molecules, high-density polyethylene, a chemically bonded chain of ethylene molecules, and polypropylene, a chain of propylene molecules. Synthetic plastics, like the four you investigated, have been in use for less than 100 years. However, people have been using natural polymers like wood and natural rubber and wool for centuries. Scientists began to investigate the atomic and molecular structure of natural polymers so they could learn how to make synthetic polymers. In 1920, the German chemist Hermann Staudinger proposed that polymers were made of long chains of many small molecules. He thought that the length of the chain was related to the physical properties of the polymer. At the time, his ideas were considered radical, and many scientists did not take them seriously. But he continued to collect data that supported his ideas. From his work, and the work from other scientists, dozens of synthetic plastics were developed. Staudinger's research on the properties and structure of plastics was so important that he actually received the Nobel Prize in 1953. Today, scientists know that changing the length of a polymer chain is not the only way to change its properties. Another way is to cross-link a polymer. You modeled this process last week when you used a model to show what happened when you mix the polyvinyl alcohol with sodium borate. Think about how the properties of polyvinyl alcohol and sodium borate were different from the properties of the cross-linked polymer, the slime. Why does cross-linking a polymer change its properties? New chemical bonds form and change the structure of molecules. The polyvinyl alcohol and sodium borate are reactants, and the result of their chemical reaction leads to the formation of a new product. The molecules and physical properties of the product are different than either of the reactants. As Staudinger found, the number of cross-links is related to the physical properties of cross-linked polymer, just as the length of the polymer chain was related to the physical properties of the polymer. If there are few cross-links, the cross-linked polymer has memory. After it is stretched, it remembers to return to its original shape, like a rubber band. If a plastic has more cross-links, the result is a harder substance that cannot be stretched and does not return to its original shape. One problem with cross-linking is that it is often difficult to reverse. In fact, the more cross-links there are in a polymer, the harder it is to break down the polymer chemically. This means that cross-linked polymers are usually difficult to recycle. A polymer that is commonly cross-linked to improve its uses is rubber. Natural rubber gets sticky in hot weather and brittle in cold weather, and it falls apart very easily. But when rubber is cross-linked, its properties change. Cross-linking rubber makes it more stable and elastic. Most of the rubber products in the world around you, from food containers to car tires, are made of cross-linked rubber. While this makes better products, the trade-off is that it causes disposal problems. Cross-linked rubber is so stable that it does not degrade. This can make recycling cross-linked polymers difficult. However, there are ways to reuse the material. For example, old tires can be shredded and made into chips. These chips are used on playgrounds, running tracks, and in road construction. Scientists and engineers have also developed ways to use old tires as a source of energy. All right, that was a lot of reading, but we finished. Make sure that your notes are completed. I can't wait to see you for Zoom. Bye.